this video I'm going to be talking about two-source interference patterns. So here we have two sources of waves, say sound waves or water waves or light waves. And the waves are going out like ripples from our sources. So I'm going to label this here source A, label this one source B. All right. Then I'm going to label a spot over here. I'm going to label this point P, and you're going to want to label it the same point, or you're going to get kind of confused as we do this. Now, I'm going to find the path length. All right, I'm going to use PL for path length for a shortcut. I'm going to find it from AP, and then I'm going to find it from B or BP. Now, if you remember, I'm going to do some things. This is a crest, a solid line is a crest, and a dashed line we're going to say is a trough. And one wavelength is the crest-to-crest distance. So I'm going to label a wavelength over here that the distance between two adjacent crests is going to be one wavelength. All right. Now, so I'm going to record my path length in distance from my source to my point in wavelength. So if I start at A, every time I get to a crest, I'm going to count one wavelength. So there's 1, 2, 3, 4, 5 wavelengths for AP. For BP, if I start at B, I go through 1, 2, 3 wavelengths. So that's going to be 3 wavelengths. So my difference in path length is going to be 2 wavelengths. And that's going to be kind of important. I'm going to draw a wave here. I'm going to draw maybe 3 cycles of it. 1, 2, 3. Now, I'm going to draw one that starts 2 wavelengths later. So it doesn't start for 1, 2 wavelengths later, but then it's going to start there, and it's going to go up and down. And you'll notice that those are in phase. If they're in phase, what type of interference am I going to get? Well, I'm going to get constructive interference and build a big wave. So at point P, I expect there to be a big wave. I'm going to draw one more, just for the sake of seeing it. So we're going to say that this is 2 wavelengths different. Let's do a different one. Let's do one that's 1.5 different. So 1.5 wavelengths different. So it's going to start, let's see, there's 1 wavelength, there's a half a wavelength. It's going to start like right here. And when it starts, it goes up, goes down, goes up like this. Now you see that that one is out of phase, all right? So it would produce destructive interference with that. So we're going to make up a little rule, okay, that if the difference is a whole number of path lengths, so if delta path length is equal to n times lambda, where n is an integer, we're going to get constructive interference. Okay? So if n is 0 or 1 or 2 or 3, we're going to get constructive interference. But if the change in path length has a half in there, so n plus 1/2 times lambda, we are going to get destructive interference because they're going to be out of phase. So if it's a whole number wavelength different, it's in phase. If there's a half a wavelength in there, it's going to be out of phase, and we get destructive. Now, point P is not the only place where we're going to get constructive interference. Okay? Every time 2 crests meet, the 2 crests are going to be in phase with each other. We're going to build a big crest. So like right here, right here, right here, right here. All of those points, there are 2 crests meeting. And the easiest one to find, or the easiest place, is when you go right down the center here, you're going to get where these crests meet. And I'm going to draw a line through those. All right, and I'm going to label that CM. CM stands for central max, central maximum. And we know that it's going to be constructive interference, everywhere along that line because that's where crests are meeting. Now, if I move over just a little bit to the right, I'm going to find another set of points where it's constructive interference. And I'm marking here where 2 crests meet, or 2 troughs meet. It's also going to be constructive because two troughs will make a very big trough, and it's still constructive. So it's constructive interference everywhere along this line. Okay? And I'm going to label that first, and I'll describe what that means in a second. But this is symmetrical, so if I have a place of constructive on this side, I'll also have it over here. So right here, oops, I had that one. Here, 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 here. So I'm going to label this too. Okay, and this is just the same as this other one, so I'm going to label that first also. This is called a first order maximum. And where I have a first order maximum, again, I'm going to get constructive interference and build a big wave. So if these are light waves, the light is going to be really bright where these maximums are. If it's a sound wave, constructive interference builds big sound waves, they're going to be really loud. Now, again, I can move over a little bit more, and I go over here, right there, and start marking all these spots. That's the one I did before by mistake. And I end up with a line like this, connecting all these places where there's constructive interference. And then the same thing, point P actually is one of them. And so I'm going to mark these places and draw a line through those. And I'm going to label that 2 for a second order maximum, 2 for a second order maximum. Now it depends on the geometry of the situation, how close the sources are together, what their wavelength is. It can change this pattern. In this particular one, it looks like I have a central maximum, first order maximum, second order maximums. It looks like if I wanted to, I could draw in a third order maximum. So it looks like we go up to 3. Depending on the geometry, we might only have 1 or 2, or we might have 5 or 6 or 7. But what you need to know is that everywhere along those lines, it's going to be constructive interference. We're going to get a big wave. If it's light, it's going to be very bright. If it's sound, it's going to be very loud. One thing I didn't want you to notice, the difference in path length for point P was 2. Well, it's on the second order maximum, and that's the way it's going to turn out. The difference in path length for everything on this first order maximum is 1, and the difference in path length along the central maximum is 0. Now there's an equation that goes with this. If I want to find like the angle here, theta, the angle between the central max and say the first order max, there is an equation that goes with that. And that equation is m lambda equals d sine theta. So in this particular equation, m is the maximum that you're studying. Lambda, of course, is wavelength. D is the distance between sources. And theta is the angle between the central max and the maximum you were studying. So if m is, if we're doing the first order maximum, m is 1, and then theta would be the angle between the first order maximum and the central max. If we're studying the second maximum, m is 2, and theta is the angle from the central max to the second order max. So it's always from the central to the one you're studying.